Hello everybody, this is Dr. Thunder. Today, I would like to show you how to solve a US high school physics competition question. So we have a sphere that falls through a fluid. Of course, you will experience a drag force that is proportional to the product of three things. First is cross-sectional area. Second is the fluid density, rho f. And third is the square of its speed. Now we suppose that the density of this sphere, rho s, is much larger than the density of the fluid, rho f. And then, of course, we suppose the sphere has a radius r, and it's dropped in the fluid from rest. So in the beginning, it's at rest without speed. So when the sphere has reached half of its terminal velocity, we want to find out the displacement is proportional to which answer, either A, B, C, D, or E. This is a relatively straightforward question. First, we can write the equation. So we assume that the sphere experiences acceleration because there's several forces that act on the sphere. The first one is the gravity mg, is downward, and then the drag force Fd, and then the buoyant force because the fluid can flow the sphere. Mg is mg, and Fd, based on the question, is proportional to the cross-section area, which is pi r squared, and then density of the fluid, rho f, and then square of the velocity. So we assume that the coefficient is C1. And then the buoyant force is the volume of this sphere, which is 4/3 pi r cubic, and multiplied by rho f, which is the density of the fluid, and then g. As the question tells us, rho s is much larger than rho f. This means mg, which equal to this expression, will be much larger than this term here. So mg is much larger than that, so we can omit this term. So we can rewrite the force equation ma about equal to mg minus this drag force. Now, we know that acceleration A is dv over dt. So A, based on this equation 2, A is, let's remove m from both sides, g minus this term. Now we assume this coefficient is C2. So dv over dt is equal to g minus C2v squared. We make it equation 3. So now we want to know the displacement. So ds is v dt. Now we plug equation 3 here. We replace dt with dv over g minus C2v squared. And then we integrate the displacement. So we remember we integrate from 0 because it's at rest in the beginning, so velocity is 0 in the beginning, and then from 0 to half of the terminal speed, and then we integrate this. So we move v into dv, so it becomes dv squared over 2g minus C2v squared, make it equation 4. So now we want to find out the terminal speed. Terminal speed is reached when the acceleration is 0, or when the mg equal to drag force. Remember we omit the buoyant force. So from equation 2 here, when a is equal to 0, then v is vt. So we find this expression for vt squared, make it equation 5. Now we begin to integrate equation 4 here. So S is equal to this one. Remember, here is the hint for the integral. So it's not difficult to memorize this. And then we plug half of the terminal speed and 0 into this expression. So eventually we get this. Now we plug Vt square, which is here. And then we also plug C2 is here. Then we eventually the displacement is 1 over 2c2 log 4 over 3. This is proportional to 1 over c2. And then remember c2 is here. So this is proportional to r rho s over rho f, which is answer B. To tell the truth, even you are very familiar with math and physics, it may take 5 to 10 minutes to work out all these equations and get these results. So we remember when we do the F equal to MA test, each question may only have a few minutes. So we introduce a quick and dirty method. So this is remember, this is quick and dirty. So it's not supposed to be very strict like the work above. So remember, now assume the sphere for a distance of h. Without considering the drag force Fd, we have this expression mgh equal to the kinetic energy, the potential energy equal to kinetic energy. So V is square root of 2gh, which is proportional to the square root of h. And now if the drag force does not have a large effect yet, then its magnitude, as the question says, proportional to the cross-sectional area, and then density of the fluid, and then square of the speed. Now if we plug V here, it's proportional to r squared rho f and h. So when the sphere is approaching the terminal speed, mg will about equal to this drag force. First we get mg. Mg is m is the volume of ball is 4/3 pi r cubic rho s g, which is proportional to r cubic rho s. Remember, when it's approaching the terminal speed, these two terms will close to each other. So Fd is close to mg. This means this term is proportional to this term. So then we have h is proportional to r rho s over rho f, which is answer B again. To prove that this quick and dirty method works, we take an example. So when we do the integration here, we integrate from the beginning to half of the terminal speed. Now assume we change this half terminal speed to 0.9 terminal speed, which is close to the terminal speed. So so we integrate from 0 to 0.9 Vt. So we do the integration, and then again we calculate. Eventually we get 1 over 2 C2 log 100 over 19. C2 again is defined as here. So this means this is proportional to 1 over C2 and proportional to, remember, C2. So proportional to R rho square over rho S over rho F. R rho S over rho F, which is answer B. So this means this quick and dirty method works. So thank you for viewing. If you like my video, please comment, like, and subscribe.